Hello and welcome to Fluid Mechanics course. This is the first lecture on Chapter 1, Introduction. In this lecture, we are going to look at sections 1.1 to 1.6, for which we'll discuss both concepts and numerical problems, and sections 1.7 to 1.9, for which we'll discuss only concepts without reference to numerical problems. I would like to begin my discussion by distinguishing between the terms solid and fluid. Now you know the meaning of these terms from everyday life, but what we commonly refer to as a solid is a substance in which the atoms or molecules have very restricted mobility or restricted freedom to move, and as a result are confined to specific arrangements over macroscopic distances. Like, for example, what I'm talking about is a block of iron that could be many meters or many centimeters in dimension, and whose atoms are all arranged in regular repeatable lattices, and the atoms are all spaced at a certain distance from each other. So that's what we will call usually as a solid. The reason we introduce solid is that we want to distinguish it against the fluid. The word fluid itself means something that can change shape or can change form easily. Fluid is a substance in which the constituents, that is the atoms or molecules, like you can think of water, for example, in which the molecules are reasonably free to move and are in constant motion, which precludes a definitive shape for a fluid, unlike a solid. And that's where the term fluid itself comes. That is, it can shift its shape as per how it is confined. Okay. Now, why does this happen? That is, if you think of solid and if you think of fluid, both are made up of atoms and molecules. They are all different states of matter. But in solids, the forces of attraction between the atoms or molecules is much stronger than the kinetic energy of these constituents. That is, you have the forces of attraction that, so each atom, if you think of each cross as an atom, they all try to move, like they all try to walk around wherever they are supposed to be around their lattice position, and they both have they all have forces or attraction between each other. That is, if I think of a potential attraction between them, it is potential is the energy with which they attract each other. That potential is usually much greater than their kinetic energy. That is the kinetic energy of each of the atoms. So in this case, what happens is the potential energy wins, and as a result, these atoms or molecules are kind of confined to wherever they are. They can't move too much. That's what makes them a solid. Okay. I'll write the potential energy leads to solid-like or solid behavior. That's what leads to the solid behavior. That's what makes them a solid. Okay. On the other hand, a fluid is one in which the intermolecular forces are weaker than in a solid, and are comparable or even less than the kinetic energy of the molecules. That is, what I mean is, if I think of each atom, they are not arranged in like a regular predictable structure. They are all moving in random velocities. That is, each tiny molecule has a velocity, and you can think of its position, its magnitude and direction. And they also have attraction forces between each other. That is, they also have forces between the molecules, and each molecule has some kinetic energy. For a liquid, the potential energy is either comparable or less than the kinetic energy, making the potential energy less dominant in this case. So if they are less dominant, as a result, the atoms or molecules are more free to move. They go around from their location for relatively long distances, and that's what makes them a liquid or a gas. Now, when I say fluid, the word fluid is used to denote both a liquid and gas. A liquid and gas behave similarly, but they do have important differences. In a gas, the intermolecular forces are the weakest, close to being non-existent. Whereas in a liquid, they are definitely weaker than a solid, but somewhat stronger than in a gas. So as a result, what happens is that if you have a solid, its density is more or less constant, or in other words, to change the density of a solid, you have to apply enormous stresses, is approximately constant. A liquid, on the other hand, is something whose shape is variable. It usually takes the shape of the container. In which it is stored. Like, for example, if you store gasoline in a tank or in a can or in a bottle, it takes the shape of the container. Its density, however, is not something that can be easily changed. Like in this case, it behaves like a solid. Like, for example, if you have water and you put it inside a piston and you try to compress the water, the change in volume of the water is going to be very, very small. Or in other words, the change in density of the water is going to be very, very minimal. You can't change the density of water that easily, and that's why most liquids are incompressible. That is, you can't compress them. Incompressible. It's a very important term in fluid mechanics. Liquids are usually incompressible. So then that begs the question, you have solid, liquid, and gas. A gas is something that is very easily compressed. You know this from everyday experience. If you have your bicycle tire and you have a valve, you inject air from the pump, and the more you inject air, you can increase the density inside. The density can be easily increased or decreased, easily changed by applying a suitable force. So liquid and gas, they both come under the same classification of fluid, but a liquid is usually incompressible, whereas a gas may be compressed relatively very easily. Okay. Now that is about their change in density. That is, we talked about solid and fluid, which is further divided into liquid and gas. We said that the solid's density, shape, and density cannot be easily changed. What I mean by easily changed is that if you apply the same force or same amount of effort to deform a solid, and you apply the same effort to deform a liquid or a gas, you are going to get much more change in shape or deformation in the case of gas than in liquid than in solid. So for the same force, gas is more deformable. That's what I mean. So liquid, its shape can be changed easily, but its density cannot be changed that easily. It's incompressible, but shape changes according to the container. It takes the shape of the container. Okay, if you put it in a bottle or a funnel or a beaker or can, bucket, whatever. A gas, on the other hand, is compressible. Its shape is not fixed. Again, it takes the shape of the container. Neither is its density. That is, you can pack more stuff or less stuff of the same gas inside a container depending on how much pressure you are applying or how much pressure the container can withhold. Like, you can think of a very common example, balloons. Initially you have no air in the balloon. As you add more air, the density goes up, and eventually the density is quite high because you pressurize the balloon. Okay, this is in relation to their shape and density. Now there is also another property of them that distinguishes them, which is solid and fluid. Like if you think of an experiment where you have a block of iron, okay, you put your hand, let's say you put your hand in here and try to move the top surface of the iron. We call this action shearing, and the force we apply is called shear force. Okay, and if you think of the iron's top surface, you are applying a force, okay, that is distributed over a certain area. You are applying a shear force F over a certain area, and this is called the shear stress. Shear force is a force that is parallel or tangential to a surface. It's parallel or tangential, and A is the area over which it acts, area over which the force is applied. And usually we give the symbol tau for shear stress. It's very commonly used. Tau is the shear force divided by the area over which the force acts. Now, that's just introducing shear force to you, or shear stress to you. Now, returning to our thought experiment where you have a block of iron if you apply a shear stress over the top surface, what would you expect? You expect that maybe the iron would be slightly deformed, maybe the plane would be slightly deformed, but it's minuscule. You can't even observe it with your naked eye. It's very, very, very tiny, that there is a very tiny deformation. Okay, deformation is a word for change in dimension. There's a very, very tiny deformation. Okay, and if you take your hand off, if you don't try to shear it, the deformation goes back to its original location. It goes back, it relaxes back to original location. Okay, it relaxes when you remove the force. Okay, same experiment. Imagine doing the same experiment where you have, let's say, a bucket of water. Okay, you have water. You put your hand in here and you try to move it parallel to the surface. Like if you apply a shear force parallel to the water, what would you expect to happen? You will see that the water is very easily displaced compared to iron. In fact, you would think that the iron was hardly displaced, or that it did not move at all, or even if it did move, it moved very, very, very little compared to water, where if you put your hand and do this like you would do on a surface of a lake when you go on a fishing trip, the water is very easily displaced compared to the iron. And that is an important property of fluids, in that fluid responds to shear stress and moves for any arbitrarily small values of shear stress. That is, you can do this experiment with a little force or a large amount of force, and you will find out that the water does move for any small amount of force that you apply. The movement is proportional to the applied force, but there is a movement for all values of the applied force. That is, even if you try to be very, very, very gentle, you will still get a very, very, very gentle response from the water. Contrast that with the iron. If you apply a very small force, you will almost see nothing. Like to your naked eye at least, there is no perceivable deformation. But for water, it is not the case. And that's what we call as the definition of a fluid. A fluid spontaneously deforms under the action of applied shear force or stress. In fluid mechanics, we usually deal with stress because we always deal on a per area basis. We deal with per area basis and its unit is Pascal. We'll see about that. But returning to fluid, which includes both liquid and gas, they both deform in response to applied shear. They both deform in response to applied shear. Where they do differ, this is a similarity between liquid and gas. Where they differ is that liquids are generally incompressible, whereas gases are generally compressible. That is, their density can be very easily changed compared to liquids. Okay, so that's the whole topic of this course. In that, we are going to look at fluid mechanics. Fluid is a substance that deforms by application of shear force. Okay, and mechanics is the study of their state at rest, which we call as statics, and movement, which we call as dynamics, movement or motion. So our whole course is the study of fluid mechanics, which includes both statics and dynamics. A fluid, by action of shear, flows, or in other words, deforms. Like, you can think of very common examples. If you have a faucet, you can have the water dripping or flowing. That's an example. You can think of many other flows. You can have gasoline flowing through a pipe, or you can have blood flowing through your body. All these are examples of flows in which a fluid moves as a collective. A flow, if I have to define that word, a fluid moving as a collection of molecules. That is, it's a very subtle concept. In that if you have a let's say you have some air in a tank. Okay. Now, if you think of each of the molecules, let's say for example it's all made up of nitrogen and oxygen. Each molecule has a certain velocity. That is, they are all bouncing around inside that tank with a certain velocity. If you think of all of their velocities, okay, all of their velocities are such that for every molecule whose velocity is this way, you can always find a molecule whose velocity is approximately opposite of that. That is, if I sum up the velocity of all the individual molecules, these will all add up to 0. Statistically, the velocities of all the molecules add up to 0. So when we just look at this tank of air, it's just there, we would think that the fluid is at rest. The fluid is at rest. What we imply by that sentence is that the fluid, or the molecules that constitute the fluid, all have velocities that more or less cancel each other out, and that they are not collectively moving anywhere. They are all centered roughly around the same point, and that their velocity, the sum of their velocity is 0. Now, if you think of the sum of the velocity and you divide it by the number of molecules, you can think of this as the average velocity of the fluid itself, of the fluid, or the molecules that make up the fluid. That is, the fluid is at rest. What that means is the average velocity of the fluid is approximately 0. Now, as opposed to this, you consider a situation where, let's say, you have the same tank, but on one side of the tank there is a fan that is sticking in, and that the fan is spinning, okay, making the molecules or pushing them to one side. And if you have like an opening through which the air flows, what you have here is all your nitrogen and oxygen, they are all randomly moving, but in addition to their random motion, they also get a push from the fan in order to move in a particular direction. That is, the velocity of each molecule contains a part that is due to the push by the fan and a part that is random. Okay. Now, going back to the concept of average velocity, if I write average velocity is the arithmetic average of all the velocities of the individual molecules, I can write this plus V random I. That is, this is the random part that each molecule has. Its value is different for each molecule, whereas this is the part that's due to the fan, that is the push. It's common for every molecule. So what I can write it is, this is n, and I'm just going to sum this from 1 to n molecules. Okay, n is a very large number usually, and I have n times u bar plus I have this summation Vri, I equals 1 to n, and this part here, this part is all the random velocities of the molecules. That is, if there is no bulk pushing, if there is no fan, these random components will all sum up to 0. It's just like a fluid at rest, and what you have is each molecule roughly has a speed that is equal to the velocity with which the fan is pushing all of them. So the average velocity of the flow in this case is equal to u, and this is what we call as the flow velocity. It's the average velocity of all the molecules. Flow velocity is average velocity of all the molecules. Okay, you contrast this with a fluid at rest, in which the average velocity adds up to 0, so that you call the whole fluid to be at rest. But if you be very, very careful, the fluid at rest means the molecules that make up the fluid have an average velocity of 0. If you take a microscope and zoom down to each molecule, you will find that they are not at rest, they are all moving, but that their velocities cancel each other out, and as a result, the fluid looks like it is at rest if you observe with the naked eye. So we say that macroscopically, or a macroscopic velocity is what we call as the flow velocity. On the microscopic scale, microscopic velocity is the velocity of the molecules that are usually random. Okay, so the flow velocity refers to an average behavior or collective behavior. This is a average or collective behavior, whereas the microscopic velocity is individual behavior of the molecules. In this course, we deal with only this. We don't try to deal with the microscopic part. That's a topic for another course, maybe future course. But in this course, we deal with only bulk or macroscopic sense of flow velocity. So when I say the fluid at rest, I mean V equals 0. When I say the fluid is flowing, it's V naught equals 0. Motion or dynamics. Okay, and we are talking about the bulk velocity of the flow. Okay, when we talk about bulk velocity, for every flow there are three important metrics that are used. One is being the length scale, that is how big or how small. Examples, we can think of an aeroplane, flow around an aeroplane, flow around a blue whale, that's really huge, flow around a car, flow around an elephant, flow around a bird, flow around an insect. Or you can think of internal flows or more technical flows, like flow through IC engines, or flow inside a engine, or blood vessels. There are infinite number of examples you can think about flows, but what distinguishes all of them is the length scale. This would be like several hundred feet. This will be maybe even, I'm not sure, but maybe like 500 feet. This could be like maybe 10 to 12 feet. Okay, and this is like a few centimeters or even millimeters. This is a few centimeters. This is millimeters. And my topic of research is related to aerosols, which are dust particles that are typically micrometer to nanometer size range. So if you think of tiny dust particles in the air, those dust particles typically have dimensions in the range of micrometers, which is 1/1,000,000th of a meter. This is another length scale that is usually one of the smaller length scales. So if you think of figure 1.1 in the book, it lists you all the possible or examples of length scales that can be encountered in real life, all the way from 10 power minus 8 meters to 10 power 8 meters. That's like 100 million meters. Okay, so look at figure 1.1a for length scales. Okay, I'll just let you look at it. Next to length scale, the next important metric we use is that of the velocity scale. That is velocity scale, which talks about how fast are you moving. Now you are used to hearing about supersonic flights or fighter aircrafts that move at speeds much greater than the speed of sound, or like warplanes, aircrafts, birds moving, again cars moving, and all the examples that I gave you in the previous topic of length, they all apply here. What we are trying to say is how fast or how slow are these things moving. You can drop some honey on the floor or molasses and they'll take forever to move because that's a very, very slow flow. You can have a human running. If that human is like Usain Bolt, he or she could be running really fast. Or you could have a river flowing. There are again countless examples that you can think of, and I want you to refer to figure 1.1b for further examples where velocities that are typically from 10 power minus 8 meter per second to 10 power 6 meter per second are listed for you. So go through those examples. So we looked at length, velocity. The other characteristic of flows is that of pressure. Now tell me some very common examples of pressure. Like for example, if you filled air in your car, my car, I need to fill it at 32 psi. And if you go to the doctor, he or she may read your blood pressure and a healthy adult is supposed to have a blood pressure that is close to 120/80 millimeters of mercury. And where else do we encounter pressure? We think of 1 atmospheric pressure. Okay, we think of high pressure situations, like for example an explosion that could lead to pressures that's like hundreds of atmospheres, and so on. You can again think of many examples and refer to figure 1.1c for different values of pressures encountered in common situations. And there, from 10 power minus 6 psi to 10 power 6 psi, you can find examples in this range. So to quickly summarize, attributes or characteristics of a flow that are important. One is that of length scale, how big, how small. The other is that of velocity scale, how fast or how slow. And third is that of pressure. How much are you squeezing your fluid together? Is it high pressure, like for example in an explosion, or low pressure, whereas it could be like outer space where the pressure is really low? So these three are the important attributes that we'll discuss for every situation of flow that we encounter in this class. Moving on to the study of fluid, before we move on to the study of fluid mechanics, what we want to understand is that there are certain basic things that we need to for a mathematical description of any science, and those are that of dimensions and units. So we want to understand what are these, and I talked about the various types of length, velocity and pressure scales that we'll encounter, and to describe those we need quantities or magnitudes as well as units or repeatable standards that can be used for expressing how many pascals or how many units of pressure or how many units of velocity or how many units of length, etc. So that we begin by thinking about what are all the basic dimensions we need to describe the physics of fluid motion. Okay. Now if you think of fluids, they are made up of molecules, and if you break it down to the very basic detail, which is that each molecule is moving as per Newton's law, let's say, we need to know the mass, the length and the time scales of motion. Mass, length and time scales of motion, because with these we can describe all higher order physical quantities. I'll tell you what I mean by that. If we have mass, length and time, M, L, T, you can describe everything else. Now what do I mean by that? If you have a length and if you have a time, the quotient of those two would be a velocity. That would be the dimensions of velocity. Okay, so if you measure length in units of, let's say, foot, and time in units of second, your velocity will have a unit of foot per second or feet per second and or meter per second. Okay. Now if you think of density, rho is defined as mass per unit volume. That is some mass divided by length cubed. So the dimensions of density is that of mass per length cubed. That is, if you take a unit mass divided by, if you take a mass and divide it by the volume it occupies, it's going to give you density. So when we want to write the dimensions of this square bracket is used to denote the dimensions of, okay, so the dimension of velocity is Lt power minus 1. You can write m power 0 or skip it, but it means that it's Lt power minus 1. Now let's think of what is force. Force is mass times acceleration, and this comes from Newton's second law. So if I have mass, that is, if I want to know the dimension of force, that would be the dimension of mass times the dimension of acceleration. What's the dimension of mass? That would simply be m. The dimension of acceleration is its length divided by time squared. So that would be the dimension of force. Now, what is pressure? We'll see it formally later, but pressure is force per unit area. Okay, so if I want the dimension of pressure, that would be the dimension of force divided by the dimension of area. We just saw what was the dimension of force, which is mLt power minus 2 divided by the dimension of area. Area is length squared. You know this. Area of a circle is pi r squared. Area of a square is L squared. So this is L squared. So the dimension of pressure would be m L power minus 1 T power minus 2. Okay. So if you refer to table 1.1, look at the MLT system, and you should be familiar with the dimensions of all the quantities listed in there, which are all typically encountered in the study of fluid mechanics. So be familiar with the quantities, with the dimensions of various quantities. The important thing is not that you memorize all that, but it's that you try to derive each of them from the definition of each quantity. Like for example, if I take power is usually defined as energy spent or energy gained per unit time. And you don't know what is energy. Energy is usually force multiplied by displacement. So you need to find the definition of that quantity and from that you try to extract the dimension of that quantity. So the dimension of energy would be whatever the dimension of force is multiplied by the dimension of displacement. So force is, we just saw ml t power minus 2 multiplied by L. So that would be ml squared t power minus 2. So if I put that back in here, so that would be ml squared t power minus 2 divided by t. So if I just continue here, that would be ml squared t power minus 3, which is the dimension of power, uppercase P. Okay, so if you check this with the entry in table 1.1, it does match up, and only difference is I use lowercase t for time, whereas the book uses uppercase T for time. I don't do that because T is also used for temperature in thermodynamics, so I try to use lowercase t for time. Okay. So you can think of dimensions are universal because the combination of M, L, T are governed by physical laws. That is, they are governed by physical laws or definitions that are universal and not on any particular set of units. Like, for example, Newton's law is F equals ma, whether you measure force in Newton or pound force. Okay, it's valid whether you measure mass in kilograms or pound mass. It's valid whether you measure acceleration in meter per second squared or feet per second squared. Okay, it's universal. So the dimensions are also universal, but what is not universal is units. Units are not universal. Like, for example, if you take 1 meter, suppose this length is 1 meter, okay, you know that about 30 centimeters is equal to 1 foot. So if I measure foot here, this will be 1 foot, this will be roughly 2, and this will roughly be 3 with a little bit of excess. Okay, so the same length from point A to point B in one set of units is 1 meter, in another set of units is 3 and perhaps 1/3 feet. Same length. Okay, so units are not universal. This is the unit and this is the magnitude. So the magnitude of how many units or how many multiples of that unit are going to be involved, that value is not universal, and neither is the unit, because they both can change. So we use unit systems. Okay, unit systems, they are predefined set of units. They are predefined set of units, and the most widely used in the world is SI, which stands for System International. And the other set of units that's commonly used in the US is that of English Engineering Units, EE, English Engineering Units. And in this course we'll use both. Okay, we'll use both. And what you need to know is the SI system is based on, for mass it's kilogram, for length it's meters, and for time it's second. The English Engineering Units is based on, it's not based on MLT first of all, it's based on force, length, time. That is, in English Engineering Units, force is the basic unit of is the basic unit and not mass, and that's how it is defined. So we deal with force in units of pounds, pound force or just pound, length in units of feet, and time in units of second. So this is the system where you use force, length, and time, and this is the system SI in which you use mass, length, and time. So what you need to be aware of, again, if you go back to table 1.1, you can derive the same set of quantities in FLT system, but as far as this course is concerned, we will emphasize only MLT. We will emphasize only MLT, and although we will solve problems in both system of units, but we will do only dimensional analysis in the MLT system. Okay. The other quantity that is commonly used in the study of fluids or thermodynamics is that of temperature. Temperature in the SI system, it's in degree Kelvin or degree Celsius, whereas in the English system it's in degree Fahrenheit. Okay. As an exercise, I ask you to find out what is the conversion factor from degree Celsius to degree Fahrenheit, and how to use these units or how to convert from one to another. We will see them through numerical problems as we use them. Okay, that's the best way to learn them. So So moving on to our analysis of fluid behavior, we need to define certain quantities that are going to help us describe fluids, and the first among those quantities is that of density. You know the definition of density from your previous classes. It is defined as the mass of a substance mass of a substance whose volume is 1 unit in some system. In some system it could be SI, it could be English, in some system. So we could say that the density of water, if you look at it, it's in figure 1.3. The density of water is, let's say, about 1000 kilograms per meter cube. What that statement means is that every meter cube of water at around 0 degrees Celsius weighs 1000 grams. Okay, that would be the density of water. And you can express density again in different unit systems. Like for example, you can use grams per centimeter cube. Like the density of water is 1 gram per centimeter cube, which is also a common measure that's been used. Or you can use you can express this in pound mass per cubic feet. You can also express this in pound mass per cubic feet, which is about 62.4. So density is very commonly used. Density is used with the symbol rho. Density is used to denote the weight or the mass of a unit volume of fluid. There are several other ways to express density. One of them is called specific gravity, which is defined as the density of a fluid divided by the density of water at 4 degrees Celsius. Water at 4 degrees Celsius has a particular property in that it exactly has a density of 1000 kilograms per meter cube, so that if you express the density of the fluid as a ratio of the density of water, you will get a simple number. Like for example, the density of mercury is 13,600 kilograms per meter cube approximately. So the specific gravity of mercury is density of mercury divided by the density of water at 4 degrees Celsius, which happens to be 1000 kilograms per meter cube, so that the conversion is easy. So this would be 13.6, and this is unitless. Why is it unitless? It's a ratio of density to density, making this quantity unitless. Okay, so that is density, and then specific gravity. Excuse me. There is one more quantity that is called as specific weight, which is the weight of one unit of which is the weight of a unit volume of that fluid. What do I mean by that? If I say specific weight has a symbol gamma, it is density multiplied by g. Now if you have mass times gravity, that will be the weight. Specific weight, the word specific, as you would have learnt in thermodynamics, the word specific means per unit mass or volume. So what we have here is kilograms. If I think of the dimensions of specific weight, that would be the dimension of density times the dimension of acceleration due to gravity, which is ml minus 3 times lt power minus 2, making this ml squared t power minus 2. Okay, so usually gamma is expressed as, suppose for water, that would be 1000 kilograms per meter cube times 9.8 meter per second squared. Okay, and this is usually written as 9800 newtons per meter cube, or 9.8 kilonewton per meter cube. The unit itself is written in a way always to give you clues about what is the quantity that you are dealing with here. We told you that gamma is the weight per unit volume. So this is the unit of weight is that of Newton, the unit of volume is that of meter cube in SI. So Newton per meter cube becomes the natural unit for gamma in the SI system. Okay, Newton per meter cube. So we have density, which is an important quantity. It can be expressed directly as density. It can be expressed as specific gravity. And it can be expressed as specific weight for the same fluid. Okay, for the same fluid you can express it in three different ways. And I mentioned previously that density, rho, I'm not going to write the word density anymore, just say rho. Rho is almost constant for a liquid, which is what makes the liquid incompressible, which means it cannot be compressed. So rho is approximately constant, and that's true most of the time for a liquid. Okay. However, the density itself changes with temperature even for liquids. That is, you know this, if you have a pot of water, you supply heat, let's say through a burner, you have water here, the water at the bottom, it gets heated up, it becomes lighter or less dense, goes up, the heavier water at the top comes down. You know this is called convection or natural convection. Okay, density is usually a function of temperature. Okay, and this is true for most liquids, if not all. Okay, it's true for most liquids, and at least for water, if you look at figure 1.3, it shows a plot of the density of water as a function of temperature. So I ask you to look at that. Okay, look at figure 1.3 for water, and you can find many more fluids listed in the appendix. Okay, now that was for liquid. For a liquid, density doesn't change too much with compression, or it cannot be changed easily at a particular temperature. Okay, for a gas, however, density is something that can be easily changed by compression. That's why we call gases that they are compressible as opposed to incompressible, which is for liquids. Okay, how exactly are they compressed and what is the mechanism, those things we'll see later. But a very common example is filling the tire in a bicycle or a car or an automobile. So the density can be easily changed. The density varies with pressure. The density also changes with temperature. Okay, and we have a law, we have the ideal gas law that describes how it changes with pressure and temperature, which says as rho, it changes with inverse of temperature. I should correct this. It's not proportional to temperature, it's inversely related to temperature. Okay, rho is pressure divided by R over T. Okay, this is called the ideal gas law. It's an empirical observation. Empirical meaning it was experimentally found out. It's not a basic law of nature. It's an empirical observation that's true for gases at low pressure and high temperature. That's true for gases at low pressure and high temperature. You would have seen this in thermodynamics also. P equals rho RT is commonly the form we use it. Ideal gas law or ideal gas equation. R is defined as the universal gas constant divided by the molecular weight of the gas. R universal is 8.314 joules per mole per Kelvin, and molecular weight is usually expressed as kilograms per mole. Like for example, for nitrogen it's 0.028 kilograms per mole. For every gas it would differ. So for helium it would be 0.004 kilograms per mole. Okay, so R is gas dependent. Okay, it's going to change with each gas depending on the molecular weight. It's calculated as 8.314 divided by whatever the molecular weight is, and it will have a unit of joules per kilogram per Kelvin. Okay, joules per kilogram per Kelvin. So at a given pressure expressed in pascals, at a given temperature, whatever it may be given in degree Fahrenheit or degree Celsius, you need to convert it into Kelvin, and you need to calculate rho as P divided by RT, which includes R, that has units of joule per kilogram per Kelvin. And if you calculate it this way, rho is going to have units of kilograms per meter cube. The reason I want you to convert any system of units to the SI is because in this equation temperature appears in the denominator. The SI system, the Kelvin scale, is such that the temperature, the minimum value of temperature is 0 Kelvin, a temperature that is not found in nature, is not found in nature. So T cannot be 0 in this system. T goes from 0 Kelvin and upwards. There is no upper limit, so T can be any non-zero number. So always use this form of the ideal gas equation with the units in these, with the quantities in these units. Okay, so this is going to be very often used. P equals rho RT, where P is the pressure or absolute pressure. Absolute pressure. Okay. The reason why I use the word absolute will become clear later. We are also going to see a gauge pressure. That's sort of like a relative pressure, whereas the P that appears in the ideal gas equation is the absolute pressure. Okay. Now continuing on, density was a measure of how heavy the fluid was, and now we need to talk about another attribute of a fluid, which is that how easily does it flow. Like for example, if you think of two fluids, let's say this is like water and mercury. You do know that mercury is much heavier, but we don't know how easily would mercury flow. Like for example, if you had an inclined plane and you dropped some liquid on here, if that liquid were water or mercury or honey, okay, You do know that from daily experience that if you drop some amount of liquid from in here or fluid from in here, they are all going to travel different lengths. Like for example, water is likely to travel the most distance because it flows easily, followed by mercury. And then maybe honey may be flowing very less because it's very thick and gooey, that it's not easy to flow. This difference between them, their resistance to flow differs with the nature of the substance, and this property or this resistance to flow is called viscosity. You say that oil is more viscous than water, or water is less viscous than oil. By that, what you refer to is how easily do they flow if they are subjected to a shear force. So the first property that we saw was that of density. The one that we are seeing now is viscosity, which is related to their resistance to flow. Density is related to their heavy or light nature. Okay. Now, what is this viscosity? How do we quantify it? Now, suppose you have like a layer of fluid. Okay, you have some fluid, let's say for example it's water or any liquid, and then you have a top surface and you have a plate that is on the top surface. Okay, you move the plate or you pull the plate with the force P. Okay, you pull it parallel to the surface of the fluid. That's why this exerts a shear force or a shear stress on the liquid. For the applied shear stress, if suppose there were a layer of liquid here, if this point by application of a shear stress tau, which is P divided by A, is moved to another point here from from B to B dashed. Okay, you can think of how much is this distance. This distance can be calculated. Let's say that distance is, for example, delta A, and this angle, the angle by which this plane has been deformed, is delta beta. Okay, now you can do some simple geometric arguments and argue that the change in angle is equal to the velocity with which the top plate moves, or the distance moved by delta A divided by the width of the whole cross section B. Okay, this is depicted in figure 1.4 and 5. Okay, delta A divided by B. This would be the strain, or this would be the shear strain. It's the change in distance divided by the cross section length. That would be the shear strain, and we want to calculate what would be the strain rate. Strain rate, which is given the symbol gamma dot. It's usually used, although specific weight also has the symbol gamma. Strain rate is given the symbol gamma dot. It's the rate at which the shear strain changes with time and calculated as a derivative. Okay, if you do this, gamma dot is delta A divided by B times delta T in the limit of delta T going to 0, and delta A by delta T, if you think of that, that would be, if this is delta A by delta T is the velocity with which this plate is moved, or the velocity with which the the surface moves. So this would be U. So we have U divided by B. That is the strain rate. Simply put it, is the velocity divided by the distance over which the velocity varies. Velocity divided by perpendicular distance. Okay, this is for a very simple example. You can generalize this for the case of arbitrary dimensions and an arbitrary fluid, and gamma dot is usually calculated as the derivative of the velocity with respect to the perpendicular coordinate. That is, if you have u and if you have y, strain rate is calculated as du divided by dy, which is the slope. Okay, du divided by dy. So this is a velocity, this is the perpendicular distance, and this quantity du by dy is also called the velocity gradient. Du by dy is also called the velocity gradient. Now, if we think of the shear stress P divided by A, it is found usually that shear stress is proportional to the strain rate or the velocity gradient. This symbol is proportional. This was found empirically, meaning it's usually seen in experiments. The shear stress experienced by a fluid, I'll write this in words, the shear stress experienced by a fluid is proportional to the strain rate, is proportional to the strain rate and strain rate, which is another word for the velocity gradient. Now, I said it's proportional. How exactly? That is, what is the relation between the strain rate and the shear stress for any particular fluid depends on a constant, a proportionality constant, which is dependent on material. That is, it varies for water, honey, molasses, gasoline, etc. It's material specific. Okay, it's material specific, and this constant mu is called the viscosity. Is called the viscosity or shear viscosity. Tau is equal to mu times gamma dot or mu times du by dy. This is the definition of viscosity. Viscosity is defined as tau divided by du by dy. Okay. The quantity mu, which is viscosity, some other names that are used for it are also absolute viscosity or dynamic viscosity. Okay. Viscosity is a property of the fluid that quantifies its resistance to flow when subjected to a shear stress. Viscosity high implies difficult to flow. Think honey, molasses. Viscosity low implies easy to flow. think water or even some light oils. Usually, viscosity of fluids is much greater than the viscosity of gases. What that implies is gases are easier to flow. They offer lesser resistance, and if you think of solids as like an extreme case of a fluid, the viscosity of a solid is practically infinity compared to that of a fluid. Okay, and what you should take note of is figure 1.6 that shows that shows the shear stress as a function of the strain rate du by dy, and that different fluids have different slopes. The slopes represent viscosity. You remember mu is tau divided by du by dy. The slope of this curve represents viscosity. So go through figure 1.6, okay, and also figure 1.8. Figure 1.8, where it is shown that the viscosity of fluids is much greater than that of the viscosity of gases. The fluids that are shown in there include like glycerin or water, and gases include air and hydrogen. So viscosity of fluids is definitely an order of 10 or 100 times more than that of, or at least even maybe 1,000 times more than that of gases. For example, I'll tell you, the viscosity of water is about 2 times 10 power minus 3 in units of Newton second per meter squared. We'll come to unit in a second. Compare that with the viscosity of air, which is about 2 times 10 power minus 5 Newton second per meter squared. Okay, this is about a factor of 100. That is, water is 100 times more viscous than air. Okay. Another aspect of viscosity that you should understand is that viscosity is a strong function of temperature. It depends on fluid temperature. And it should also be noted that viscosity is not a strong function of pressure. That is, viscosity, unlike density, does not change with pressure. Like to recall, rho is P over RT for gases. Okay, rho is a function of T for liquids. Viscosity is a function of T only, not P, for both gases and liquids. And that's what is shown in figure 1.8, the temperature dependence. Okay, temperature dependence. The temperature dependence of viscosity is usually expressed in the form of an empirical relation. The word empirical means something that was found out in the lab by repeated experimentation and statistical analysis and has no reasonable physical basis to be true. Empirical observation is that viscosity follows a power law, that is C T to the 3/2 divided by T plus S. This equation is called the Sutherland's law of viscosity. Sutherland's law or equation. Don't get carried away by law. Law doesn't mean it's always true. It's just Sutherland's equation, and this is equation 1.10 in the book. It's also modeled by a different equation. It's kind of like mu equals E, dE power B over T, and this is called Andrad's equation, and this is equation 1.11. You should be familiar with these relations. So look at equation 1.10 and 1.11. Okay. The last aspect about viscosity that we should understand is that I told you that if you have shear stress plotted as a function of the strain rate, if you have a straight line, the slope of that straight line is what you will calculate as the viscosity of the fluid. That is, for a given value of shear, for a given value of a strain rate, you have a corresponding value of shear stress, and that it is proportional. That is tau 2 divided by tau 1 is equal to gamma dot 2 divided by gamma dot 1. This will make it as a simple fluid or Newtonian fluid. It was Newton who first discovered this property of fluid, okay, and it carries its name still. This is true for common liquids like water, oil, crude oil, air, etc. Okay, these are Newtonian fluids. There are some fluids for which the graph doesn't look straight, or the graph is not a simple straight line. You have tau, gamma dot, or du by dy, or the strain rate. If you have just a simple straight line, it's a Newtonian fluid. Okay, you could have fluids that have their profiles that look like this or like this. Okay, these are non-Newtonian fluids. First of all, they are not Newtonian. Their slope is not a simple straight line. Now, if you look at this number 1, what do you infer? As you increase the strain rate, the amount of shear stress increases less slowly. That is, if you take this versus this, okay, to produce more and more shear stress, you need to produce higher and higher strain rate. Okay, this will be an example of a shear thickening fluid. That is, it thickens as you shear it. Shear thickening fluid. Example, quicksand. Something that the more you deform it, it gets harder to deform. Shear thickening means the more you deform it, the harder it gets to deform. It becomes harder to deform. On the other hand, number 2 is called shear thinning, because once you start deforming it, it becomes easier to deform. Shear thinning fluids are, for example, like many colloidal dispersions, or even like paint. Once you start applying the paint, it becomes easier to apply. Initially, it may be a little hard, but once you stir it, it becomes easy to apply. That would be an example of a shear thinning fluid. The last kind is that of something that has a y-intercept. We call that the yield stress. You need to deform it to a certain extent, and then it starts to move. Okay, it has a threshold or a yield stress. You need to apply at least that much stress for it to start moving. Until then, it will behave like a solid. So for tau less than tau yield, it will behave like a solid. A very common example for that is that of toothpaste. If you just put it on your toothbrush and leave it there, it will retain its shape for a long time. But the moment you start brushing it, it deforms and becomes like a fluid. So that's an example of a fluid, and the name given to that is Bingham plastic. Okay, these are different types of fluids. In this course, we will deal almost only with Newtonian fluids. Okay, but you should be aware of the different other types of fluids that are out there, and maybe in the future you will encounter them. And this is depicted in figure 1.7. So take a look at figure 1.7. Okay. Now I talked about density. I talked about viscosity. The symbol that's commonly used is mu. Here the symbol is rho and mu. The other types of expressing density are specific gravity and specific weight. The viscosity is expressed usually as dynamic viscosity, which is defined as tau divided by du by dy. Okay. Now, if we were to calculate the units of viscosity, this is usually expressed in Pascal divided by velocity is in meter per second and y distance is in meters. So we have a unit for viscosity in Pascal second. Okay, Pascal second is very easy to remember, and I want you to calculate what are the dimensions of viscosity, which is the dimensions of Pascal or pressure. Let me write it as the dimensions of shear stress divided by the dimensions of strain rate. Okay, so what is the dimension of shear stress? Shear stress is a kind of a force per area. So it's force per area, and force is, if you forget, it's mass times acceleration divided by area. So mass is m, acceleration is lt power minus 2, and area is L squared. So you have ml power minus 1 t power minus 2. And du by dy, if you forget, this is a velocity per length. So this is lt power minus 1 divided by L, or t power minus 1. So the dimensions of viscosity would be ml power minus 1 t power minus 2 t power divided by t power minus 1, or mass per length per time. Okay, that would be the dimensions of viscosity. Other names used for viscosity are absolute or dynamic viscosity. Okay, so you have density rho, viscosity mu, dynamic viscosity. Okay, a new quantity called nu, or given the symbol nu, is called kinematic viscosity. Nu is defined as dynamic viscosity divided by density. It's also very commonly used in the description of fluids. We specify, instead of specifying density and viscosity separately, we specify the kinematic viscosity. Kinematic viscosity has units of Pascal second divided by kg per meter cube, and if you simplify this is going to be Newton per meter squared second divided by kg per meter cube, and Newton is kg meter per second squared divided by meter squared second kg per meter cube. So if you do the if you cancel out kg, if you look at this is going to be meter squared per second. Okay, that is the unit of kinematic viscosity is meter squared per second, or the dimensions of kinematic viscosity is length per time squared. Kinematic viscosity is also called momentum diffusivity. Momentum diffusivity It's a measure of how fast momentum diffuses through a medium. Like when you learn heat transfer, you will also learn about thermal diffusivity. Wherever the word diffusivity appears, there will be a quantity that measures how fast diffusion happens, and that will have units of meter squared per second. So to just wrap this up, this is density in kg per meter cube, dynamic viscosity in Pascal second, and kinematic viscosity in meter squared per second. Okay, these are the quantities that you need to be familiar with while solving problems. So we saw density, which is a measure of how heavy a fluid is, the viscosity, the dynamic viscosity, or just the viscosity, which is how much resistance a fluid offers to shearing force or motion. And then we saw what is kinematic viscosity, which is a ratio of dynamic viscosity to density. The next property we want to see is related to the compressibility of fluids, and it's the bulk modulus of a fluid. The bulk modulus is defined the same way for a fluid or a solid. It's a concept from the study of elasticity, which is that bulk modulus is defined as the change in pressure to the change in the relative change in volume. Okay, so delta P is the stress or pressure that is used to squeeze or expand a certain material, which could be a fluid or a solid, and delta V over V is the volumetric strain or change in volume to the original volume. Okay, for a fluid, this is a general definition. For a fluid, it's defined as the change in pressure to the change in density. This is the relative change in density. Okay, and usually we want to think of what will be typical values of the bulk modulus. Bulk modulus is usually very high for solids and liquids. Okay, it's not as high for gases. Why? If you look at the definition, it's the change in pressure to the change in density. Okay, now for a solid or liquid, we can almost say that the change in density is 0 for a solid or a liquid, and that the change in density is finite for the same delta P. If you apply the same amount of pressure to squeeze a liquid or a solid or a gas, the gas will undergo more change in density than the solid or liquid, making this very high for a solid and relatively low for a gas. Okay, I mean, it's all relative. That is, if you somehow travel to the center of a planet like the Earth or Jupiter, where the compression is really high, you can even compress a solid to a certain degree or a liquid to a certain degree. Under reasonable pressures that we encounter on the surface of the Earth, solids and liquids behave like they are as though incompressible, whereas gases are compressible, and the bulk modulus is a measure of how compressible they are. Okay, and one more metric that is used in the study of compressible fluids is the speed of sound. Which is calculated as the square root of the change in pressure to the change in density, and this is given by equation 1.19 in the book. This is the bulk modulus divided by the density, and it is equal to square root of K RT for an ideal gas. This part is true only for an ideal gas. This is true for any fluid. Okay, you just need to know these concepts. This is equation 1.20. The next property of fluids that we are interested is that of vapor pressure, which is that if you have a liquid and if you have a confined cylinder or a confinement that allows the liquid to evaporate but accumulate here, what you have is here is a vapor of the liquid. Okay. Vapor pressure is the pressure exerted by the vapor with pressure PV, and if the pressure of a fluid P, if the pressure of a fluid P falls below the vapor pressure PV at that temperature, then you have what is called as evaporation or boiling. That is, the liquid spontaneously boils when the pressure drops below the vapor pressure. It's a property that is used more in the study of thermodynamics, as well as cavitation, which is formation of vapor bubbles in a flowing fluid, but we won't talk about much in this course. The last property that we are interested is that of surface tension, which is the force between a layer of liquid and a surface along the line of contact. Like, for example, if you have a droplet that's lying on a surface, if you think of the top view, here is the top view, you have a circle that is the line of contact. It is the force that acts along the line of contact. It is the attraction between the droplet and the surface acting along the line, acting along the line of contact. And this is a very important property of liquids and gases that leads to the formation of bubbles, interfaces, and droplets. It's a very intriguing property. It has a lot of important implications in everyday life. We won't touch too much of this in this basic course, but you are welcome to look at section 1.9 to see some basic applications of what is surface tension. So the last three topics that we discussed, section 1.9, 1.8 and 1.7, are going to be somewhat qualitative in nature, that you'll just look at only the definitions and not going into too much of numerical problems. The sections 1.1 to 1.6 will be detailed in terms of both numerical problems and conceptual questions that we'll discuss in class. Now, since this is the first lecture, I would wish to conclude by giving you some basic instructions, which are: kindly watch the video lectures. Kindly watch the video lectures. Read relevant sections of the text. And be prepared when you come to class. for class. During class, we will solve example problems. We will not go through the concepts again. This is nearly a 2-hour lecture that we won't repeat in class time. We'll just use it for example solving. Start working on the homework, which has problems related to the topic, and each homework is roughly 10 to 15 problems. Okay, so please start working on them immediately. This whole exercise or this whole semester, it's going to be that you watch these lectures before coming to class, and then during class you ask questions and you do examples and you have discussions with me as well as other students. We are not going to teach you the lectures again in class. Kindly remember that. So with that, I'll conclude this first lecture on chapter 1. Kindly start working on homework 1, and we'll meet in class during the first week to discuss this. Thank you.